Greetings, Dr. Dan with Optimal Optics, here to introduce Unit 4, Reflection at a Spherical Surface. So I downloaded an image of a circle from the internet, and I placed the center of the circle at C. This is the place where you would put the point of the compass. I'm not talking about the compass that tells you where due north is. I'm talking about the compass that you use for drawing circles. The point would go there, and then the pencil at the other end would be used to inscribe the circle. Now, any arc on this circle has that same center of curvature. So because we're sending light in from left to right, the left side of the circle is our spherical surface that we're reflecting off of, and it's got a center at C. The normal is drawn through C. If you remember your geometry, when you construct a tangent at that point, the radius or the diameter of the circle makes a 90-degree angle with the tangent. So this normal is making a 90-degree angle with the surface at that point. We call the part of the surface that crosses the optical axis, we call that A. That's also called the vertex of the surface. We randomly place our object M on the optical axis. We already said that C is the center of curvature of the mirror. The radius of that surface is defined as AC. That's the distance from A to C, the vertex to the center, and that is a positive direction for a convex surface. We arbitrarily place our image M prime on the optical axis. I'll show you later how to determine exactly where it is. And that's an extension back from the ray that's reflected from M. It is called a virtual image because the light does not actually get there. It just seems to come from that point. N is the normal. We define the object distance as U, and that's the distance from A to M. That's a negative direction in this case, and U prime equals AM prime, the vertex to the image, and that is a positive direction going from left to right in this case. Keeping your signs straight is really, really important in optics. When you plug in these variables into your equations, you must have the proper signs or you'll come up with the wrong answer. Okay, we'll draw another optical axis. We'll draw a concave mirror. Now, a good way of remembering concave versus convex is to remember that light's traveling from left to right for our course. And after traveling so far and so fast, it can take a rest inside this cave that we've constructed. So a concave mirror is shaped like this cave. Convex goes the opposite way. Okay, we'll arbitrarily say the center is at C, A is the vertex, and our object is at point M. We'll send a ray to the normal from M, and then we'll reflect it. So the angle of incidence equals angle of reflection and form image M prime over there. Incoming ray, outgoing ray, angle of incidence equals the angle of reflection. Remember, the angle of incidence is the angle between the incoming ray and the normal. The angle of reflection is the angle between the reflected ray and the normal. U is the object distance, which goes from A to M. U prime is the image distance, going from A to M prime, and the radius of curvature is the distance from A to C, vertex to center. So AM is a negative direction going from right to left. This is a real image, right? The light actually passes in front of the mirror. If you put a screen there, you would get an image on that screen. U prime is also negative, going from A to M prime, and the radius is negative going from A to C. And remember, the normal goes through the center of curvature. Here's another optical axis. And another concave spherical surface with the vertex A. We're going to send in a parallel ray of light, parallel to the optical axis. And remember that rays are parallel when they come from optical infinity. We define the point on the optical axis where parallel rays are focused as the focal point, and we label it capital F. We'll place our center there, we'll place our object there, and we'll say our image is formed at that point. Again, I'll show you later how to determine exactly where the image is formed. So, we define our focal length as the distance from the focal point to the vertex. That's FA, and for a concave mirror, that's a left to right positive direction. We can also define our object and image distances with respect to the focal point rather than with respect to the vertex. So we say x is the distance from the focal point to the object, FM, like the radio band. And the way we've drawn it, that goes from right to left, and it would be a negative number. The image distance also is measured from F, this time to M prime. And again, going from right to left, that would be a negative value. Good formula to remember is focal length squared equals the product of those two distances, x prime. And just to reinforce, capital F is the focal point, and it's the place where rays from optical infinity are focused. It happens to be halfway between the center of curvature and the vertex, halfway between C and A. So the focal length equals negative r divided by 2. The minus sign is there because the focal length is measured from the focal point to the surface, while the radius is measured in the opposite direction from the surface to the center of curvature. This is the mirror equation, really important. 1 over u plus 1 over u prime equals 2 over r equals negative 1 divided by f. Another optical axis. And we'll draw a convex spherical surface. And we'll place our object arbitrarily there. We'll call the vertex A. The focal point and the center are on the right side of a convex surface. We'll send in our parallel ray, which will go through the focal point. We'll also construct our normal that goes through the center. And we'll send a ray from M to the normal. And we'll say the image is formed at M prime, which is the extension back of the reflected ray. Again, that would be a virtual image. Now, for a convex surface, the focal length FA will be negative because it goes from right to left. And the way we have the objects and images drawn, x, which equals fm, is also a negative direction, and x prime, which is fm prime, is also a negative direction. Now let's give our object and image some height. We'll create arrows, and we will say that the object height is y and the image height is y prime. So the magnification for a spherical surface when you reflect off of it is y prime divided by y, which equals negative u prime divided by u, or f divided by x, or x prime divided by f. The magnification is positive for erect images, and it is negative for inverted images. And the absolute value of m, if it's greater than 0 and less than 1, it means you have a smaller image. That's called minification. Now, here are the rules for the construction of objects and images at a spherical mirror. First thing you do is you draw your optical axis. Then you can draw a straight vertical line for your mirror. You don't have to draw a curve. You'll know if it's a concave or convex mirror depending on which side you place the center. So if it is a concave mirror, you place the center and the focal point on the left side. And if it's a convex mirror, you place the center and the focal point on the right side. So a good rule is to place the center about 2 inches from the vertex, which you mark as A, and then you put the focal point about 1 inch from the vertex A. Now, you draw a horizontal line about 1 inch above the optical axis. That's your parallel ray, and send its reflected ray through F, and you can extend it back in both directions if you want. Then you draw a vertical arrow object between the optical axis and the horizontal line above that you just drew. You can put a little arrow on the top, and you draw a line from that arrowhead through C. Now that's the normal. That means the angle of incidence equals the angle of reflection, which equals 0. So the reflected ray reflects back on itself. Where that line intersects the line through the focal point, that is where the arrowhead of the image will be formed. And you draw that image, and you have it there. And you can look at it, and you can see right away if it's real or virtual, if it is magnified or minified, and if it is erect or if it is inverted. It's a good way of checking your answer when you do the equation. Okay, you should always draw a picture first, and then if you see that you have a real inverted image and your equation gave you a virtual erect image, you know you've done something wrong, and you can go back and check your answer, check your work. So let's see exactly how this works. We're going to construct some objects and images here. Again, I will draw my optical axis, and I'll place my mirror here. It's a curved mirror, but it's much easier to draw a straight line than a curve. And by placing my center and my focal point on the left side, we know it is a concave mirror. F halfway between C and A. And we'll draw our horizontal line from infinity, send it through F, and we'll extend it both ways like that. And we're going to construct some objects now. A better idea might be to make our objects different colors and have their images match the colors so that we can differentiate them more clearly. So let's make our first object blue. And we're going to send a ray now from the arrowhead through the center and see where it intersects the line through the focal point, right there. And that's where the arrowhead is. So we see our image is inverted, it's real, it's in front of the mirror, and it's also smaller. So object 1 produces image 1 prime. Now, let's place our next object at the center, different color, and we see when we send the line through the center that our image is formed in the same place, it's the same size, but it is inverted. Okay, let's place our next object 3 between the center and the focal point and send our ray through the center and see where it intersects the line through the focal point. We'll have to extend that one back a little bit, and we see we now have an inverted, real, magnified image. So as we get closer and closer to the focal point, the image gets bigger and bigger. Now let's see what happens when we put our object at the focal point and draw our line through the center. And we see that this line is parallel to the line through the focal point. That means they never meet. And that means that image 4 prime is at infinity. Now let's place object 5 between the focal point and the surface and draw our line through the center. And look what happens now. Now we have a virtual image. It's formed on the right side of the mirror, and it's also magnified. So this concave mirror is a makeup mirror. My mom used to have one. She would get close to it and see her magnified face to put on makeup much more accurately. It's interesting, though, because as you get further back from the mirror, once you reach the focal point, you don't see anything. You're looking into infinity. You can pretend you're Buzz Lightyear to infinity and beyond. And so you can actually see infinity by looking from the focal point into a concave mirror. As you get further back from there, you can see yourself again, but you're upside down, which would make it a little difficult to apply makeup properly. Now you see as you get closer to the mirror, the image on the other side also gets closer to the mirror from the back, until if you put your nose against the mirror, the image of your nose would be pressed up against you on the opposite side of the mirror. Now let's do the same thing for a convex mirror. We will draw objects and images and see where they end up. Okay, again, we'll draw a straight line for our convex mirror, but we'll know it's convex because the center and the focal point are on the right side. Label the vertex A. We'll draw our horizontal line from infinity going through the focal point. And now we'll draw our objects and images in different colors and see where they reside. So we'll do our blue first object, 1. Draw a line from the arrowhead through the center, and we see that the image is erect and smaller and virtual. So on the right side of the mirror. So a convex mirror is a side view passenger mirror in your automobile. And you'll always notice inscribed in the mirror, it says objects are closer than they appear. And the reason for that is the image that you're looking at looks smaller, and as something gets further away from you, it appears smaller. So you would think that what you're seeing in the mirror is further away than it really is. So you might ask, why don't they bother putting a plane mirror in the passenger side mirror like they have in the driver's side mirror? And the reason is that you get a bigger field of view if you have a convex mirror. It's similar to looking inside a room through a window from the outside. You can see the entire room if you press your nose against the window. But as you get further back, you see less and less of the room. Your field of view decreases. So by looking in a convex side view mirror, you're able to see more stuff because it's all smaller. You can fit more stuff in there. And so you can see more cars and hopefully be more likely to avoid an accident if you look in the convex mirror on the side. I installed a ceiling mirror above my bed in my bedroom, and it says anatomical objects are larger than they appear. Now we're going to draw some virtual objects now. You might ask, how can we get a virtual object? Well, you can use a lens to focus the light as if it appears to be coming from those places. So if we place a virtual object 2 behind the mirror between the surface and the focal point and send the light through the center, we see now we get a real erect, magnified image, 2 prime. Let's place our next object at the focal point. You can probably predict what's going to happen as we send the ray through the center. That ray is parallel to the line going through the focal point. Therefore, they never meet, and 3 prime is at infinity. We'll place our next object 4 between the focal point and the center. And now we have a virtual, inverted, magnified image. We'll call that 4 prime. We'll place our next object at the center, object 5. You can probably, again, predict what's going to happen. We have our image also formed at the center, same size, just inverted. And we'll place one more object out in right field, object 6. And you'll notice that the image is getting smaller and getting closer to the mirror.